In this video, we're going to be talking about section 5.5, multiple eigenvalue solutions. This is going to be part 1 of section 5.5, where we'll just cover the first 3 pages of the notes, and then we'll cover the last 2/3 pages of the notes in a second video to come. So again, this is talking about multiple eigenvalue solutions. In section 5.2, we discussed how we can find solutions via the eigenvalue method, assuming we have either distinct real eigenvalues or we have complex eigenvalues. In this section, we talk about if we have repeated eigenvalues and what happens if we do not obtain n linearly independent eigenvectors. So let's take a look here. To begin with, we need to talk about what it means to have higher multiplicity. So an eigenvalue is of multiplicity k if it is the k-fold root of the characteristic equation as stated. So back in chapter 3, we had discussed that we could have roots of our characteristic equation that had higher multiplicity, and we just handled that duplication by tacking on a c1 plus c2x plus c3x squared. And so we want to see if there's some kind of an analog here in the eigenvalue method. So the next definition says an eigenvalue of multiplicity k is complete if it has k linearly independent associated eigenvectors. So the thing to keep in mind here is we're assuming that we have multiplicity k, and even if we have this repeated multiplicity of an eigenvalue, if somehow we can still find k linearly independent eigenvectors, this is a good thing, and that's what we're going to call complete here. So remember, our goal is to find n linearly independent solutions so that we can take the linear combination to find a general solution. So having a complete eigenvalue is something that we desire. All right, so we have a remark here that says, look, if all of our eigenvalues are complete, then we're in business. We can follow the method from section 5.2, which said as long as you can find these linearly independent solutions, you can take the linear combination to find the general solution. So let's take a look at example 8. We want to find the general solution. In this case, we have a 3x3 matrix, and we're just going to follow the eigenvalue method from 5.2. So I just want to note that there is additional white space on page 2, the top of page 2, to complete this example. So you can see here all of this space at the top. So you shouldn't have to cram too badly. So let's begin by setting up our characteristic equation, which is the determinant of a minus lambda I equals 0. We want to solve that equation. So that's going to give us 25 minus lambda, and I'll just fill in the rest of the first column. 12, negative 5 minus lambda, 6, and 0, 0, 13 minus lambda. All right, now if you'll recall in class, a lot of times I poo-poo what I like to refer to as the basket weaving technique of finding determinants. That is where you just multiply all of the diagonals in one direction and subtract off the product of all the diagonals in the other direction. It's a valid way to compute a determinant, but the reason why I dislike it is because it's going to make things difficult when we're solving for the roots of the characteristic equation. So I'm going to stick with my general method of expanding along a row or column and using cofactor expansion. And in this case, the clear winner is to expand along the third column because of these 2 zeros right here. So those 2 zeros just zero everything out. And so what I need to focus on then is this term right here. So my determinant becomes a negative 1 to the third row plus third column times that value in that entry. And then I want to strike through that row and column, and I want to multiply through by the cofactor matrix. That determinant would be 25 minus lambda, negative 18, 12, and 25 minus lambda. All right, and then of course, this characteristic equation has to equal 0. So that I get a -1 to the 6, which just becomes a +1. I'm going to recopy this 13 minus lambda and then compute the determinant of the 2 by 2, which is a 25 minus lambda times a 25 minus lambda, and then double negative plus 18 times 12 equals 0. So 18 times 12 is what, 216? And 25, oh, whoops. Let's go ahead and fix this up here. Shouldn't be a 25, but should be a -5. I apologize. So I have -5 times 25 gives me a -125. And then I have a -25 and a +5. So -20 lambda plus lambda squared. And I had said that that was going to be 216. All right, now since we already have the 13 minus lambda factored out, we don't want to do anything with that. We're just going to leave it as that factored form. But we would like to further factor everything inside the brackets. So if we combine, I get lambda squared minus 20 lambda. 216 minus 125 gives me a total of 91. And miraculously, 91 is not prime. It looks like it is, but it has factors of 13 and 7, which are going to work out perfectly for us. So 13 minus lambda, lambda minus 13, lambda minus 7. All right, so we have lambda 1 equals 7, and lambda 2 equals lambda 3 equals 13. All right, let's take a look first at lambda equals 7. And we want to find the associated eigenvector. So what I'm going to do is I'm going to look up above at this matrix right here, and I'm just going to replace lambda with 7. So instead of 25 minus lambda, I get 25 minus 7, which is 18. So I'm going to input that in here. I will recopy the lower two terms, -18 and 6. And then do the same for the next column. So -7 or -5 minus 7, it's going to be a -12. So I get 12, -12, and 6. And then finally 0, 0, and 13 minus 7 is 6. Now I want to multiply by some arbitrary vector, which I'm going to call ABC, and this is the eigenvector that I seek. And this is always going to equal 0. So first I'll note that these top two equations are going to give me the same thing. So I'll just write one of them, 18a plus 12b equals 0. And the bottom equation is giving me 6a plus 6b plus 6c equals 0. All right, so I have two equations with 3 unknowns. And what I'm going to do here is, let's just go ahead and simplify this first. This is 3a plus 2b equals 0. And then a plus b plus c equals 0. What I'm going to do is, you'll note that I have two equations but 3 unknowns. However, C only occurs in one of the equations. So if I focus on this equation, 3a plus 2b equals 0, let me pick some convenient values for a and b that will satisfy that equation. And my second equation, a plus b plus c equals 0, will force a value for c based on my values for a and b. So I am going to choose that a equals 2. And then that'll give me B equals -3. All right. So again, I made this choice, A equals 2. If I plug that in right here, that gives me a 6 plus 2B equals 0. So I conclude that by my choice of A equals 2, that forces B to be -3. Now, remember I had that A plus B plus C equals 0. Now I have 2 minus 3 plus C equals 0. So this then forces C to equal +1. So just by making this one choice, I was able to recover a B and a C that would then satisfy both equations. So it's important that you pick a value that works for you. Everybody's eigenvector might look a little bit different, but I chose A equals 2 so that I wouldn't have any fractions. So I'm going to stick this, I'll write it in red, I'm going to stick this up here. I now have an eigenvector for lambda equals 7, and I have 2, -3, 1. All right, so here's my eigenvector for lambda equals 7. I knew that one wasn't going to be too bad because I don't have any higher multiplicity, but remember I only have one other eigenvector that had a multiplicity 2, and so let's see how that's going to work out here. So now let's take a look at lambda equals 13. So if I plug it in up above, 25 minus 13 is 12. So I have 12, 12, 0 across the top. I have -18, and then -5 minus 13 is -18. So now I have -18, -18, 0. And then along the bottom, I have 6, 6, and 13 minus 13 is 0. So then I will just have my random eigenvector here, ABC, and equate this to 0. And in this case, all three equations are equivalent. They are all going to give us A plus B equals 0, or in other words, A equals -B. What's important to note is that C doesn't occur in any of these equations. What that means is C can be anything we want, and it doesn't matter because we don't have any relationships as to how C relates to A and B. So we call C a free variable. The fact that C is a free variable is what's going to save us in this particular case, that we're going to be able to come up with two linearly independent eigenvectors because of that free variable. All right, so here's what I'm going to do. I'm going to now pick my eigenvectors. And remember, the only forbidden eigenvector is the 0 vector. So I can't have any eigenvector being 0, 0, 0. However, I could choose A and B to be 0. And since C is a free variable, I can choose C to be whatever I want. So I'm going to pick it to be 1. All right. And now for my, for my third eigenvector, or my second eigenvector for this eigenvalue, I can let C be 0, and then I just need for A and B to add up to 0. So I'm going to choose 1 and -1. Because I chose these zeros to occur in opposing places, this ensures that V2 and V3 are linearly independent because of those zeros. All right, so at this point, I can now write out my solutions. So my individual solutions are the following. For x1, my eigenvector was 2, -3, 1. and that had an eigenvalue of 7. And then for x2, I had 0, 0, 1, e to the 13 lambda. And finally, my third solution was 1, -1, 0, also with 13. Oh shoot, and I wrote lambda and I meant to write t here, so let's fix that. There we go. All right, so these are our 3 solutions. I won't go through and check that these are linearly independent, but of course you could go through and compute the Wronskian if you didn't believe me, just to confirm that these are in fact linearly independent. And then let's write our general solution. I'm going to write it in scalar form. Oops. So x1 of t equals, so I'm going to take c1 of the first solution plus c2 of the second, et cetera, et cetera. So I have 2 c1 e to the 7t. I'm going to write a plus 0 here just to indicate that we don't get anything from the second equation. And then I have a c3 e to the 13t. x2 of t is a -3 c1 e to the 7t plus 0. And it's actually minus c3 e to the 13t. And then my final scalar solution is a c1 e to the 7t plus c2 e to the 13t plus 0. So these 3 scalar equations form my general solution. All right, so this is kind of in the best case scenario where we have a repeated eigenvalue, but even in spite of that, we're able to find enough linearly independent solutions to come up with the general solution. Unfortunately, life is cruel, and that isn't always the case. And so remember, if we go back up top, we had defined the term complete, which means we have a repeated eigenvalue, but yet we're able to find these enough linearly independent eigenvectors. Complementary to that is the term defective. So now we're going to say, look, suppose we have an eigenvalue of multiplicity k, where that k is something larger than 1. We call an eigenvalue defective if it is not complete. In other words, we're not able to find k linearly independent eigenvectors. If this is the case, supposing it has p linearly independent eigenvectors, then the number of missing eigenvectors that we need is called the defect. So if you take k, the number of times it's repeated, and subtract off the number of linearly independent eigenvectors you were able to find, that's called the defect. So to finish off part 1 of section 5.5, we're going to talk about how to solve systems that are defective with a multiplicity 2 eigenvalue. So if you have an eigenvalue whose multiplicity is 2, the only way you can possibly be defective is if you only admit 1 linearly independent eigenvector. So that's what we're going to look at now. All right, so step 1 here, suppose that lambda is a defective eigenvalue of multiplicity 2. And we want to go through and find the single non-zero eigenvector v1 associated with lambda. The most important phrase in step 1 is write it in generality. Do not choose values for A, B, and C specifically. Leave it in generality, and then we'll force those out later on. All right, next step is to find a non-zero vector v2 that satisfies these equations. All right, so this first equation here looks similar to the equation that we use to find eigenvectors, except for we have this square here. So that square is what's different, and then what we do is we utilize this equation to force the values in V. So this now chooses specific values for V1. So we had originally written it in generality, and now we have forced it. And then based off of these two steps, we get two linearly independent solutions. The first solution is just like the others have been. You take your one eigenvector that you will able to identify from the repeated eigenvalue. And then the second one, we see kind of a similar setup from section 3.3, where we have this repeated root of our characteristic equation. And so instead of a C1 and a C2 tacked in here, now we have our V1 and V2, where that's determined back up here with this chain. All right, so let's take a look at this with our next example, problem 4. All right, so we have this 2x2 system, and we want to find the general solution. Let's begin by setting up our characteristic equation. And so that's going to be 3 minus lambda, 1, negative 1, and 5 minus lambda. And of course, we equate that to 0. This is a 3 minus lambda times a 5 minus lambda plus 1 equals 0. Let's go ahead and expand. Lambda squared, let's see, we get a minus 5 and a minus 3 is a minus 8. A 15 plus 1 is going to be 16 equals 0. And so this factors to lambda minus 4 quantity squared. So we get lambda 1 equals lambda 2 equals 4. So we have multiplicity 2. All right, so at this point in time, we don't know if this eigenvalue is complete or defective. So we have to check that. So what we're going to do is we're going to move along and use our standard equation to find eigenvectors. All right. And so what we have here is a 3 minus 4, which is negative 1, 1, negative 1, and 5 minus 4 is 1. Multiply by an arbitrary eigenvector, AB, and set this equal to 0. And so once again, we see that these are equivalent. And both of these equations are giving me A plus B equals 0, or in other words, A equals negative B. All right, so any eigenvector that I am going to find here is going to be of this form. It's going to be of the form negative B, B. And it doesn't matter what value I pick for B, if I pick B equals 1 or if I pick B equals 500, all of those eigenvectors are going to be scalar multiples of each other, which is bad. That means they won't be linearly independent. All right, so the important thing to note here is we want to leave this in generality. All right, do not choose a value for B at this point. We will force B out here in a moment. All right, so let me just scroll back up here. We have now completed step 1. We found an eigenvector in generality associated to lambda equals 4. So now we're going to move on to step 2. So first I'm going to look at this equation here, lambda or A minus lambda I squared V2 equals 0. So I want to find a V2 that satisfies this equation. So A minus lambda I already computed right up here. So let me recopy that. I want -1, 1, -1, 1, and then times itself, because I want it squared, times some V2, and I'm going to denote that as, let's call it CD. I want to find a vector CD that's going to satisfy this matrix equation. So let me go ahead and carry out this multiplication. This is going to be, if I do row by column, I get -1 times -1 is a 1, plus -1 is 0. Now if I do the next column, it's the exact same thing, so I'm going to get a 0. And now moving to row 2, column 1, I get -1 plus 1, which is 0, and then I'll get the same thing back again. Oops. Now, if I step back and I look at this equation, I say, okay, if I take the 0 matrix times any vector, of course I'm going to get the 0 vector back out. So the reality here is this is going to be true for any V2 vector, right? This equation is true no matter what I choose for C and D. So the only vector I cannot choose is the 0 vector, because that's forbidden for eigenvectors. So choose any other vector in the world that you want other than the 0 vector. So I'm going to choose 0, 1. That's my favorite vector. So V2 is 0, 1. This was my choice. And now based on my choice of vector V2, I'm going to use it to then flush out my V1. So remember V1 back up here? We left it in generality. I'm going to let V2 force what B is going to equal. So let's scroll back up here and look at the second equation we want to use is this one. So let me copy that down. The A minus lambda I times V2 is going to equal V1. So A minus lambda I V2 equals V1. All right, and so that is -1, -1, 1, 1 times my V2. And we're going to hope that this gives us back out V1. In fact, we do more than hope. It should, unless we made a mistake somewhere. So let's carry out this multiplication. This is going to be a -1 plus 0 and a 1 plus 0. So in other words, this forced B to equal 1, right? If you look back up at this guy right here. Okay, so that's good, right? This is kind of a nice checkpoint to say, look, when I multiplied A minus lambda I times V1, I did in fact get a vector that was of the correct form for V1. So that's always a good sign. So then finally we can write out our solutions. So we've moved on now to step 3. The first solution is as it always was, V1e to the lambda t. But then our second solution looks a little bit different here, V1t plus V2, that whole quantity times e to the lambda t. So let's write those out. I'm going to actually write them up here since I kind of ran out of room. All right, so our vector ended up being -1, 1 for V1. And this was e to the 4t. And then our x2 is going to become our V1t plus V2 e to the 4t. Now remember, these are the individual solutions. we now need to use them to write out the final general solution. And so the general solution, x of t, is c1 x1 of t plus c2 x2 of t. Oops. And so if I write these out in scalar form, what do I get? I get a negative c1 e to the 4t plus c2 negative t plus 1 e to the 4t. And similarly, x2 of t equals c1 e to the 4t plus c2 t e to the 4t. And I'll box that in as my final answer. All right, so in the next video, we'll finish off the end of these notes, which is going to talk about how to handle these situations if your defect is larger than 1, in this case 2. So stay tuned for the second half of this lecture.